3x plus 2y equals to 6. Typically, the way we try to tell if something is a function of x is to solve for usually y, right? So typically we're asking, is y a function of x? If we can solve for y in a normal way, which I'll kind of talk more about in a minute here, then yes. In this case, we totally can, right? You can write 2y equals negative 3x plus 6, and you can divide by 2. So that y is equal to negative 3 halves x plus 3. So yes, here we can express y as a function of x. So we're good to go. Let's look at the next one. So the next one is y squared equal to x plus 1, I think, yeah. So the problem with this is that we can try to solve for y, but if we take the square root of those sides, so the square root of y squared equals the square root of x plus 1. The problem with the square root of y squared is it's not just y. The square root of y squared is actually the absolute value of y. Which means that, so really I'm kind of taking the long route to get to saying that y is equal to plus or minus the square root of x plus 1. Which means that y is not a function of x, because to be a function, the way functions work is you input one value for x and you get out one and only one value for y. But in this particular case, if I let x equal 3, for example, if x is 3, y could be plus or minus 2. That's not a function. Right, and we can see it up here as well, right? If x is 3, 3 plus 1 is 4, y could be positive 2, 2 squared is 4, or y could be negative 2, negative 2 squared is also 4. So this is not a function. If you graphed this as well, you would see it's not a function. Like the graph of y squared with x plus 1 looks like, let's see, looks like, I think it looks like, sorry, I think it looks like x is 0, y is 0. Yeah, sure. It looks like this. Looks like a sideways parabola. And we can see that this graph is failing the vertical line test. If you draw a vertical line, or if you can draw a vertical line that passes through more than one point. Right, so this could be the line x equals 3, and it's passing through the points 3, 2, and 3, negative 2. So definitely not a function of x. Then we have the other two. So this one actually, so y cubed minus y equal to x is not a function of x. It's a little harder to explicitly do what we just read, but I think it's actually possible to actually solve for y here. And you can't get y in terms of just x, which is also a really good indicator that you don't have a function of x. So we can't solve, we can't isolate y here. In this case, what I would probably suggest doing is actually trying to graph it to really see. So often what I typically do is right now graphing that is kind of hard, but not if I use Desmos. So if I use Desmos, let me show you guys. Hopefully you're all familiar with Desmos. If you're not, you'll get to be. It's a very useful tool. Let me share my screen. Yeah. So here is good old Desmos, and I'm just going to graph y cubed minus y equals x. I might write it as x equal to y cubed minus y, but you can probably write it either way. But you can definitely see, oh yeah, that is failing the vertical line test. Right in the middle here, right, there are definitely 3 values of y corresponding to 1 value of x, specifically x equal to 0 and y equal to either 1, 0, or negative 1. So sometimes you can't solve for y, but you can still see graphically that, oh yeah, definitely not a function of x. That's kind of cool. So the middle two are not. No, you weren't expected to use Desmos. Like you certainly could if you wanted to, Marshall, but I'm just trying to show you that in addition to seeing this and saying, well, if I can't solve for y, I'm pretty sure it's not a function of x. another way you could actually verify that for yourself is to go ahead and try and graph it. And you could try and graph it by hand, right? It's not like impossible to graph by hand, but it is, you know, it takes some effort to graph by hand. But that is typically, if we can't solve for y, we can also use the graphing to verify that it may or may not be a function of x. Let's compare this to the last one. So the last one was y cubed minus 1 equals x. And here we can actually solve for y pretty easily. So we get y cubed equal to x plus 1. And now we're going to take the cube root of both sides. The cube root of y cubed is going to equal the cube root of x plus 1. Now, I want to point out a really important difference. When you take the cube root of something cubed, you just get the thing. So the cube root of y cubed is always just y. So I solve for y as a function of x. I'm not getting y equal to plus or minus the cube root of x plus 1. I'm just getting y equal to the cube root of x plus 1. So here we definitely have this in the function. Of x. It is worth pointing out that when you take an odd root of the same odd power, you just get the thing. So if you take, you know, like the fifth root of x to the fifth, it's just equal to x. Or the seventh root of x to the seventh, it's just equal to x. But if it's an even root of the same even power, you don't get that. So if you take like the fourth root of x to the fourth, you don't just get x. You get the absolute value of this. And the same is true for any other even power. Now, here, just to kind of make sure everyone's cool with this, because I've definitely seen this be a point of contention for people in the past. Let's just look at an example with some numbers. I'm going to look at the square root of x squared. Specifically, I'm going to look at the square root of 5 squared. Now, I know this might seem silly, but what's 5 squared? 25. And what's the square root of 25? That's right. It could be, it might be 5. Okay, but now negative 5 squared is also 25. And the square root of 25, still 5. So this kind of shows you how, look, whether I put in a positive number or the same corresponding negative number, either way, the output is still a positive number. Well, I know another function that does that. It's called the absolute value. So it is really actually literally true that the square root of x squared is the same as the absolute value of x. And that's actually true for the nth root of x to the n power for any even value of n. On the other hand, it is not true for odd roots, right? The cube root of x cubed. So if I want to do like the cube root of 2 cubed, that's the cube root of 8, which is 2. But if I do the cube root of negative 2 cubed, that's the cube root of negative 8. And again, when you're looking for the cube root of a number, you're saying, what do you multiply by itself 3 times to get negative 8? And the answer is negative 2. Negative 2 times negative 2 is 4, times negative 2 is negative 8. So odd roots and powers kind of retain the sign, whether it's positive or negative. Even roots and powers do not. They kind of make everything positive. So good to know. I'm going to end the poll. I don't know why it's showing me that, but I don't really care. Close the poll. Let's get back to more problems. I do feel so there's a couple more problems on this PS1 handout that have to do with finding y as a function of x. So let's just take a look at those. So I think they are worthwhile. And again, if there's anything specifically you guys want to see, feel free to let me know by saying it or writing in the chat. But I'm just going to kind of pick and choose various pre-calculus things here. And then we'll go back to domain after I do these functions of x. So here's another one. A lot of these are similar to the ones I just gave. Some of them are different. So x minus 2y cubed equal to 4. So again, our job here is to try to solve for y. In this case, we totally can. I'm going to subtract x, so negative 2y cubed equals 4 minus x. I'm going to divide by negative 2. So y cubed equals 4 divided by -2 minus x divided by -2, which I would probably simplify. I'd probably write that as -2 plus x over 2 or plus 1/2 x, either way you want to write it. And then I'm going to take the cube root of those x. And we know that when we take the cube root, it doesn't give us this plus or minus into the square root or any even root. So we're going to get y equal to the cube root of -2 plus x over 2. So y is a function of x, because for any one x input, we get one y output, right? The thing that we're looking to make sure doesn't happen is if you put in one value for x and you get more than one value for y. Jared, out of the way. So the next one. I think the next one's the one I really actually wanted to do, except I'm looking. The next one's not that exciting. The next one is also pretty similar to the one we did. So what do you guys think? Yes or no? Is this x equal to y plus 1 squared minus 4? Is this a function of x? Yes or no? You can even use the little the reactions, right? The yes or the no reaction. Like I would like you to use the yes or no reaction. Yes, this is a function of x, or no, this is not a function of x. Oh, cool. It kind of shows, oh, that's neat. I had never noticed that before. So instead of showing me, well, it does show me who's saying yes or no. It also like counts them all up for me at the bottom. The problem with the yes or no's, which is a new problem for Zoom, is that they don't persist anymore. Right? So they don't actually, it doesn't stay saying no. They all go away after a while, which means I can't like actually see all the people who did it. But it looks like everybody said no. You're right, it's not. And typically having y to an even power is a pretty good bet. Not always for sure, but it's usually a pretty good bet if you're not going to have a function of x. So if we try solving for y here, we get 4 plus x equal to y plus 1 squared. And then square rooting both sides, we get the square root of 4 plus x equals the square root of y plus 1 squared, which is really the absolute value of y plus 1. Or we can just take the short path and say y plus 1 equals plus or minus the square root of 4 plus x. And right there, that plus or minus is the killer, right? So we end up getting y equal to -1 plus or minus the square root of 4 plus x. And we can see that for just about any value of x within the domain, y is going to end up having two different values. If x was 0, y would be -1 plus or minus 2, which would be -1 plus 2 is 1, and -1 minus 2 is -3. So yeah, clearly, and again, if we graph this, you can see it's a sideways opening parabola. It's definitely going to fail over the line test. Now for a couple more that are a little more interesting, a little dissimilar from our previous examples. We've got this one. We've got xy minus 3 root x plus 5y equal to 2. And at first glance, you might be willing to bet that this is not a function of x, but we shouldn't be so sure. So again, we're going to try and solve for y. In this case, since we've got multiple instances of y, we should group all of our y's on one side and all of our other stuff on the other side. So I'm going to leave xy plus 5y on the left, and I'm going to add this 3 root x on the right. And then I'm going to factor out the y, because I'm trying to isolate y. So I've got y times x plus 5 equal to 2 plus 3 times the square root of x. And then finally, y equal to 2 plus 3 times the square root of x divided by x plus 5. And for any x that's in the domain, meaning x has to be greater than or equal to 0, it looks like this is just going to spit out one value, right? If x is 4, you're going to get 2 plus 3 times 2, right? Square root of 4 is 2, over 4 plus 5. That's one thing, right? There can be multiple things. So yeah, this is a function of x. And that's usually, right, that's usually the thing we're looking for. Can you solve for y equal to x, stuff with just x in it, and not have there be some plus or minus is usually the thing that messes up a lot of these potential functions. And the last one is the absolute value of y equal to x plus 3. And we know pretty clearly that the absolute value of y equal to x plus 3 means y could be positive or negative. So This here says y can be positive x plus 3 or negative x plus 3. And that's going to be a problem, right? So if x is 0, for example, y could be positive 3 or negative 3. That's not a function because one input's giving you multiple outputs. Cool. So not a function. And I should say, right, later on in either 16b or 16c, we start talking about how y can be a function of x or x can be a function of y. So while you might say that in this particular example, or actually, let me go back, right, in this example, y is not a function of x, but it is true in this example that x is a function of y. That's going to come later on. At this stage, we pretty much, when we're talking about something being a function, we are always thinking about x being the independent variable and y being the dependent variable. So if we're ever asking, is something a function, we always mean it in the way that is y a function of x. Did you have a question, Marshall?
Yeah, so one of the things that I've just never seen before when you were solving the problem is to get rid of the absolute value, you made the other side plus or minus.
Right.
Because most of the time I've just seen other teachers say like, oh, if it's a square root, then you just assume it's like plus or minus. But how did you so if it's an even root, like you can always assume that like it's gonna be the absolute value, and then like to get rid of that absolute value, you do the plus or minus to the other side.
Right.
Okay.
So yes, you said all the correct things. But in general, right, so absolute value is really defined to be, so what you're really saying here, right, is that the absolute value of y is equal to x plus 3, it means y can equal that, right, because the absolute value of x plus 3 is equal to x plus 3, but y could also be the negative of that. So the absolute value of negative x plus 3 would equal x plus 3. Assuming x plus 3 is positive, right? For this to have solutions, this has to be positive. So the absolute value of a positive thing is equal to the thing. The absolute value of a negative thing is equal to the positive of that thing.
Okay, thank you.
You're welcome. And more generally, that's how we, like, for example, if someone said, solve this equation, absolute value 2x minus 3 equals 7, the way we would solve that is we would say, oh, 2x minus 3 equals positive 7, or 2x minus 3 equals negative 7, because the absolute value of 7 is 7, and the absolute value of negative 7 is still 7. So that's kind of really where my thought process is coming from there. Okay, let's take a step back and look at a few domain questions, because there's some slightly more interesting ones than the ones we did last class. So we had done last time, we had started off with this one, f of x equal to the square root of x plus 5. And so, in fact, I should point out, last time we talked about kind of, and we gotten that, x plus 5 is greater than or equal to 0, x is greater than or equal to -5. So the domain, if we're going to write using the interval notation, is bracket -5 to infinity. And then I also just want to kind of write up the general domain guidelines. There are 3 types of functions that have domain restrictions. There are 1 or 2 other kind of very special functions that have specific domain issues, and those are really inverse trig functions, which we'll talk about later on. But for the most part, the 3 types of functions that have domain issues are fractional things, right, where you might be dividing by 0, square roots, and logarithms. So the 3 domain issues we have are if your function is some sort of fraction. So I like to write it as, I don't really care what's on top over some stuff, right? We don't care what's on top. Then what we do is we exclude where the stuff is equal to 0. So whatever you've got, if you have a denominator, we know that the denominator can't be 0. And then if we have a function that's equal to the square root of some stuff, we know that the stuff has to be non-negative. So we're going to say that the stuff has to be greater than or equal to 0. And thirdly, if your function is a logarithm of some stuff, it doesn't matter what the base is, any usual base, if you have the log base b of some stuff, it's almost the same as a square root, except we can't have 0 as well. So in this case, our stuff has to be strictly greater than 0. So those are the 3 things I'm always looking for if someone asks me about domain. Is there a place where I might be dividing by 0? Is there a place where I might be taking a square root? Is there a place where I have a logarithm? Any of those 3 things should set off your sentence and be like, oh, I need to do something because there is a domain restriction. So let's look at this next problem, which I can do here, yeah. So the function is x plus 2 over the square root of x plus 5. So there's actually kind of 2 different things at play here. We have division by something. So we know that this thing here, square root of x plus 5, we want to exclude where it's equal to 0, right? We don't want it to equal 0. So we can solve this. We can probably just see that the solution is -5, but we can also square both sides. X plus 5 equals 0 squared is equal to 0, and then subtract 1. So we don't want this number. We want to exclude x equal to -5. Additionally, we know that anything inside of the square root has to be greater than or equal to 0. So x has to be greater than or equal to -5. So we can use the number line if we want. We don't have to. There's -5. I want everything that's greater than or equal to -5, but then I also don't want -5. So I actually want everything that's just strictly greater than -5. So here the domain ends up being -5 to infinity, with the parentheses on the -5 to indicate that we do not want -5. We want everything up to it. Be careful. I've definitely seen people do a problem like this and say, okay, I want everything bigger than -5, so that means I'm starting at -4. So I've seen people incorrectly say that the domain for this is -4 to infinity. And that's not correct because it doesn't get you everything you need, right? There are a lot of numbers between -4 and -5, right? -4.1, -4.2, -4.3333, right? There's in fact an infinite number of things between -4 and -5. So we need to make sure we capture all those. And when we capture them is by saying, oh, well, I want everything up to -5, just not -5 itself, which is what this parenthesis tells us. Right, let's do some more. I'm going to leave this up for a minute and come back to it. Alrighty, let's see here. Where'd you go? Sure. Let's look at the flip. Let's look at f of x equal to the square root of x plus 5 over x plus 2. So again, we have 2 things to deal with. Thing 1, we have to exclude where the denominator is equal to 0. So we're going to exclude x equal to -2. And thing 2, again, we need the stuff inside the square root to be non-negative. So we need x plus 5 to be greater than or equal to 0, which means we need x to be greater than or equal to -5. Let me do real quick before I forget. So at some point during the class, I typically take a screenshot of all the participants just so it's easier to fill in the attendance later. Don't worry, I'm not like doing anything nefarious with the screenshot. I'm just going to look at it to then put all of your attendance in Canvas sometime later today. But I also will go check the Zoom report as well, just in case you maybe came in or out before or after I took the screenshot. So don't worry, I will definitely make sure to capture your attendance. If for some reason you get marked absent and you were there, just let me know and I will definitely fix it. So we want everything bigger than or equal to -5, but not -2. So I personally like drawing the number line. I think it's helpful. Sometimes it's really actually necessary. Here you could probably get away with not drawing it, but I want to exclude -2, and I want everything that's bigger than or equal to, meaning to the right of, including -5. So I want all of this, not that. So we're gonna have to write this as 2 intervals because there's a break between this section and this section. So everything from -5 to -2, excluding -2, and then I want everything from -2 to positive infinity. So there's the domain of this function. X can't be smaller than -5, like -6 would be a problem, because -6 plus 5 is -1. You can't make the square root of a negative number and get a real result. And -2 is also obviously a problem. Plugging -2, you get division by 0. But anything else is fine, right? -3, totally cool. Plugging -3, you get the square root of 2 on top, you get -1 on the bottom. Square root of 2 over -1 is a real number. If you plug in something like 5, square root of 10 over 7, also a real number. It's not a nice number, right? It's not a lovely integer that's easy to express, but right, f of 5 is the square root of 10 over 7. It's certainly a real number. It's a little bit bigger than 3/7. Okay. Let's look at the next one. Oh yeah, the next one. A little, I forgot. I don't have the chat. Get into the chat. Form of line. Oh yeah, sure. Totally. I think yeah, definitely. You can certainly do that even next. Let me do these last 2 domain questions, then we can definitely do some line stuff. So let's see, the last 2, yeah. So here's a function. This one is definitely gonna take a little more effort. Yeah. The square root of x squared plus 7x plus 10. So I want to be very kind of explicit about this one because I've definitely seen many people over the years do problems like this kind of the wrong way. So I want to say that x squared plus 7x plus 10 has to be greater than or equal to 0. And I'm going to factor. So I'm going to say that x plus 5, you really don't want to do something like, I've seen people bring this 10 over here. We don't want that. If we're trying to solve an inequality, we really want it to be greater than or equal to 0, because it's usually not too terrible to try and see where a thing is positive, meaning it's greater than 0, and where a thing is negative, meaning it's less than 0. So this fact is that x plus 5 times x plus 2. And then what we can't do is set each part to be individually greater than or equal to 0. Right? It's not correct to say that x plus 5 is greater than 0 and x plus 2 is greater than or equal to 0. I've seen people do that. Then they get something like x is greater than -5 and x is greater than -2. And so then they're like, okay, here's -5, here's -2. I guess I get all of this. We do not get all of this. In fact, we specifically do not get, I think the part in the middle, no, the part in the middle is actually fine. I think we don't get the end parts. All right, I'm not sure actually. I think we don't get the part in the middle. Yeah, because the part in the middle, right, would be if x, like for example, if we plug in -4, -4 plus 5 is positive, -4 plus 2 is negative, and a positive times a negative is negative, which is not greater than or equal to 0. So we don't get any of the numbers between -5 and 2. We do get all the numbers bigger than -2, but we also should be getting all the numbers less than -5. So here's what we should actually be doing. So once you have factored, so what if you have an inequality greater than or equal to 0 or greater than 0, you want to factor the side as much as possible. And then you want to find the zeros, or the places that make it equal to 0, which are x equal to -5 and x equal to -2. And we want to put those on the number line. And then we want to test each of the intervals. So however many points are on your number line, you have one more than that interval. So there are 2 points on my number line. That means I have 3 separate intervals. So I'm going to pick a point over here. You can pick anything you want. I'm going to pick something ridiculous, like 1,000. I'm not actually going to figure out what the numbers are. I'm just going to see if things are. Sorry, I keep like my hair is like getting in my eye. It's killing me. Anyway, sorry. I'm going to pick 1,000, but you can also pick like 1 or 0. But 1,000 plus 5 is definitely positive. 1,000 plus 2 is definitely positive, and a positive times a positive is definitely positive. And that's true for any number over here, right? Once it's positive over here, it has to be positive everywhere over here, because the only change from positive to negative is to go through 0. And the only places it's equal to 0 is -2, -5. So you can pick 1,000, or you can pick 1. 1 plus 5 is positive, 1 plus 2 is positive, 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 positive. And then we can pick something in between -5 and -2, like -4. -4 plus 5 is positive, -4 plus 2 is negative, a positive times negative is negative. And then we can pick something over here like -10. -10 plus 5 is negative, -10 plus 2 is negative, and then negative times negative is also positive. I want the positive parts because I want it to be greater than 0. I also want the endpoints because I also want it to be equal to 0. So my domain here is everything from -infinity to -5 inclusive, bracket, union, -2 to infinity. This makes a lot of sense if you think about what the graph of x squared plus 7x plus 10 looks like, right? That's the function that we have, but just that inside portion, if you think about its graph, it's a parabola, right? If you look at y equals x squared plus 7x plus 10, it's a parabola with x-intercepts -5 and -2. And it kind of looks like, I know I'm giving myself not a lot of room here, but it kind of looks like this, where it's definitely positive to the left of -5 and positive to the right of -2. But between -5 and -2, it's definitely under the x-axis, negative. Okay, sorry. So let me do one more. Let me do the last domain question here, and then I'll definitely do some line stuff. I might have to ask for some clarification. Domain's kind of a big deal. It's definitely something that's always kind of, I mean, a lot of this class, I know a lot of this class is definitely about derivatives and rates of change, which we haven't talked about yet because we have to build that up. But that's definitely what your teacher has said in her notes, right? Like that is where, or at least that's what Dr. Thompson said. I don't know about Dr. Wynn. But definitely, right, we are looking with an eye towards thinking about how functions change as time is changing, or how something is changing as something else is changing. But underlying all that is the fact that we are dealing with functions, right? Calculus, although about rates of change, is about rates of change of functions. So we really have to be very familiar with how functions work. And one big piece of that is knowing how the domain of the function works. So look at this last example, and then we'll move on. So here's one more function. It's 1 over the square root of x plus 5 minus 2. So again, we have two things going on here. Thing 2 is that this x plus 5, right, the stuff inside the square root has to be non-negative. So that once again, x has to be bigger than or equal to -5. And the first thing that probably we'll look at is that the denominator can't be 0. So we have to exclude where the entire denominator, square root of x plus 5 minus 2, equals 0. I would probably solve this by actually doing the work. So I'm going to add 2. So square root of x plus 5 equals 2. Then I'm going to square both sides and get x plus 5 equal to 4. So x is equal to -1. So I want to exclude that value. Because if x is -1, -1 plus 5 is 4, square root of 4 is 2, 2 minus 2 is 0. We can't divide by 0, so that's the problem. So here our domain. In fact, let's draw the number line. So again, -5 and -1. It is important that they are in the correct place compared to one another. I want everything bigger than or equal to -5, but I don't want -1. So I want everything from -5 to -1, parentheses, union, parentheses, -1 to infinity. Right. Sure. So let's talk about lines for a minute. Maybe more than a minute. This person to glass. What time is it anyway? Oh yeah, we got loads of time. We got so much time. So line equation, sure. So there's a number of ways we could ask to find the equation of a line. Let's do this one. So let's find the equation of a line passing through the points And for the person who asked me about lines, please do, if I'm not doing exactly what you're looking for, let me know and I will clarify them. So passing through the points, let's say the points -4, 1, and 5, what make it 7. Why not? So to find the equation of a line, you always need 2 pieces of information. Specifically, you need a point. Great, we've got a point. We've actually got more than 1 point. And you need a slope. And the slope might be given to you in a number of ways. It might be you have to find the slope between the 2 points using the slope equation. You might be given another line and said, well, the lines are parallel, and that's going to find the slope. Here, we're going to find the slope by using the slope equation, which is that the slope n is equal to the difference in the y's over the difference in the x's. So in this case, it's going to be the difference in the y's, so 7 minus 1, or 1 minus 7, either way you want to do it. But whichever way you do it, for the y's, you have to do it the same order for the x's. So if I did 7 minus 1, I have to do 5 minus -4. That's going to be 6 divided by 9, which reduces to 2/3. Now, the way you can find the equation of the line, in my opinion, there's 2 ways of doing this. One way is to write it in the the point slope form. So point slope, where you can just say y minus whichever y coordinate you want to pick. I'm going to do the same. I'll use this one. Y minus 7 equals 2/3 times x minus 5. You could also write it as y minus 1 equal to 2/3 times x minus -4, which would be x plus 4. However, a lot of the time, teachers prefer people to write their lines in the standard slope-intercept form. Also because that way you can write y, you're explicitly writing y as a function. So if I want to, I can solve either one of these for y. I can say, so let's do this first one. Y equals, I'm going to distribute this 2/3. So I'm going to get 2/3 x, and 2/3 times -5 is minus 10/3. And then I'm going to add 7 to both sides. And then putting these together, 7 is equal to 21/3. So I can write y equals 2/3 x, and -10/3 plus 21/3 is 11/3. We also could have used the other point slope version and gotten the same answer, right? If we do it here, y minus 1 equals 2/3 x plus 2/3 times 4 is 8/3. And then if I add 3/3 to both sides, I get 11/3 here, just like I got here. This is one way of doing it. The other way is just starting with, oh, okay, sure, totally, Marshall, I got you. We can talk about the general form as well. I'm going to erase this here for a second. I don't want to do this more. So let's talk about it. So yeah, there's 3 things we can do. So there's the point slope, which is either one of these. There's the slope intercept, which is this. I personally, even if I'm finding the slope intercept form, I typically prefer to start with the point slope form and then just solve for y. But other people like to start with, say, y equal to mx plus b, and then plug in either point to find b. That's also perfectly fine. If I plug in 75, I'm going to get 7 equal to 2/3 times 5 plus b, and I get 21/3. 2/3 times 5 is 10/3, so minus 10/3 plus b. So we do end up getting b is equal to 11/3 once again. But there is another form which doesn't look like really either of these. I think I've got enough of them. So the general form, or yeah, the general form. Sometimes people get the names backwards, but yeah. So the general form of a line looks like ax plus by equals to c. And typically, a line written this way, usually x and y have integer coefficients, but it's not absolutely required. It's just nice. So I was going to try and make this look like this. Yeah, so I guess the question is, what's the easiest way if you're trying to find the equation of the line to make it look like the general form? Yeah, what would I do? I'm just trying to think, like, I would probably get to the slope intercept form, and then here's what I would do. I would bring my x to the left. So I would have, from this one here, I would have -2/3 x plus y equal to 11/3. And then I would try, if everything had fractions, I would try to multiply both sides by the common denominator. So I'm going to multiply everything by 3 and get -2x plus 3y equal to 11. That's how I would write it. This is one way you could write it. It would also be correct to multiply everything by -1 and say 2x minus 3y equals -11. So both of these are probably correct ways of writing it in the general form. Does that kind of address your question, Marshall? Cool. Let's do another one. So let's say I want to find the general form of the line perpendicular to 3x plus 4y equal to 12, passing through the point I don't know, to make sure it's not a point that's on this, 3, 1. Sure, that seems reasonable. Okay, so as I said previously, to find the equation of a line, no matter what, you need a point and a slope. I've got a point, and I know that I can find the slope. I know that my slope is supposed to be perpendicular to the slope of this line. What's the slope of this line? Well, here's what I do know. The slope of this line is not immediately obvious, right? So that's kind of the less nice thing about the general form, is you can't immediately read the slope of the line just by looking at the equation. I mean, maybe you can. You could. I think everyone probably could, in their head, solve for y here and figure out what the coefficient of x would be, right? If we subtract 3x, we get a -3x over here, and then if we divide by 4, you get -3/4. So the slope of this line is -3/4. You could also do the work, right? You can say 4y equals -3x plus 12, and then divide everything by 4 and get y equal to -3/4 x plus 12 divided by 4 is 3. But all that really matters is that the slope of this line is -3/4. So if the slope of the line is -3/4 and our line is perpendicular to that line, what's the slope of our line? Yeah, +4/3. And I've got to imagine there's probably, so you could probably do something tricky, right? Like if you're trying to find a general form, if you know the slope, I feel like there's a way to make it work where, like, well, I guess here's what we could say if we really care. This is maybe not super pertinent, but if you have the general form, which is ax plus by equal to c, and you solve for y, you get by equal to -ax plus c. You get y equal to -a over b x plus c. So if a is the coefficient of x and b is the coefficient of y, the -a over b is your slope. So 4/3 is equal to the slope. We could think of this as the -a over b, which means you could say that the b value is 3 and the a value is -4. So that feels like a convoluted way you could figure it out, but you could in fact say, all right, my general form is going to be -4x plus 3y equal to, and then we can plug in this point, x is 3 and y is 1, to figure out what it actually has to equal. I don't like this. This feels kind of weird, but it would work. So I plug in 3 I get negative 12. We plug in 1, I get, but let's just plug it in. So plug in 3, 1, and we're going to get negative 12 plus 3 equal to negative 9. So that's our equation. I feel like it's a weird way of getting there, but this equation has the right slope, right? If we solve for y, we definitely get y equal to 4/3 x, and it definitely goes to this point, because if you plug in 3, 1, you get negative 12 plus 3 equal to negative 9. Now, if someone asked you a question like this, right, to find the general form, I wouldn't do this, right? Even though I know that my slope, right, that my slope is negative a over b, and you can figure out what a and b are, and a is the coefficient of x, b is the coefficient of y. I don't think I would do it this way. I think I would instead do it the more normal way, which is I would probably say, okay, yeah, my slope is 4/3, great. Y equals 4/3 x plus b. Let's find b by plugging in this point. So 1 equals 4/3 times 3 plus b. Cancel the 3, so 1 minus 4 equals b, so b equals negative 3. And then I would write the equation. So I would write my equation as y equals 4/3 x plus negative 3. I would subtract this over, so negative 4/3 x plus y equals negative 3. And then I would multiply both sides by 3. So negative 4x plus 3y equals negative 9, which is exactly what we got there. So either way of doing it's fine. I feel like, although I know this first way that I did it works, it seems super funky to me, so I probably wouldn't do it that way. But yeah, that's how you find the general form. If you had irrational coefficients like square roots, this would not look so nice. But don't imagine someone's going to ask questions like that. Right. Yeah, good question. Thank you, Marshall. I appreciate it. You guys are all welcome to ask questions. Let's see, what have I got on the board here? Some graphing. All right. Well, that's actually, oh yeah, I see someone has a question. Go ahead, Diana.
Can you do an example for a parallel line?
Oh, totally. Yeah, definitely. Parallel lines, in my opinion, usually easier, but yes, for sure. So let's say we want to find the equation of the line parallel to, let's make it easier. Let's say it's parallel to y equal to 2/3 x plus 5, and it has it with an x-intercept of, I don't know, 6, negative 6. Okay, so as usual, we need a slope and a point. We've got both. They're just trying to hide from us. If lines are parallel, so if my line is parallel to this line, and this line has a slope of 2/3, what slope does my line have?
The same one as that one.
Right. Parallel lines have the same slopes. I should say that's true unless they're vertical lines, because vertical lines have undefined slopes. We don't really say undefined things are the same. But yeah, if two lines are vertical, they are parallel, even though they don't have a slope. And then we need a point. And our point is the x-intercept, which is the point -6, 0. Right? If it's the x-intercept, the y-coordinate 0. So then I'm going to do it the point slope way, which is y minus the y-coordinate equals your slope times x minus the x-coordinate. And while some people are fine with leaving it like this, I think in this case especially, since you've already got a 0 over here, it really makes sense just to rewrite this as y equal to 2/3 times x plus 6. And I would probably distribute the 2/3 here and say y equals 2/3 x, and then 2/3 times 6 is going to be 4, or 12/3, which is 4. So that's how we do that one. Yeah, good question. So I talked a lot about domain, but what about range? Range is also something that comes into play sometimes. So there's a couple ways you can find range of a function. One way is graphically. So for example, if I said, what's the range of, I don't know, f of x equal to x squared minus 4x minus 5, we could find the range by graphing this. It's a parabola. It opens upwards. We know there's some bottom where the vertex is. Let's actually graph it though. So the vertex, we can find the vertex by finding the x coordinate is negative b over 2a, which is negative 4 over 2 times 1, which is 2. The y coordinate of the vertex is the function evaluated at the x coordinate. So it's going to be f of 2, which is going to be 2 squared minus 4 times 2 minus 5. That's 4 minus 8 is negative 4, minus 5 is negative 9. That's really all you actually need to know to answer this question. But if I was going to actually graph the thing, I'd also find the y-intercept, which if I plug in 0, I get negative 5. And I would also find the x-intercepts. So I set the function equal to 0, x squared minus 4x minus 5, and I can factor that as x minus 5 times x plus 1, because minus 5 and positive 1 multiply to negative 5 and add it to negative 4. So my x-intercepts are x equal to positive 5 and x equal to negative 1. So if I was graphing this, let's see. So my vertex is at 2, negative 9, right? So 1, 2, and then negative 9, translate that right there. And my y-intercept is negative 5. My x-intercepts are positive 5 and 1. So it's going to look something like this. It's not going to look great because it's not. Oh, it's okay. I've drawn better. So the domain is all the possible x values for the function. The domain of this function, do we see any issues? We do not, right? There's no fraction for division by 0. There's no square roots. There's no logarithms. So if you don't see any of the 3 functions that have domain issues, it's pretty safe to say that the domain is everything. So the domain of this function is all real numbers, which you can either write as, typically in interval notation, we say it's parentheses negative infinity to infinity. If it's all real numbers, you can also say it's a fancy R, which is just an R with 2 vertical lines instead of 1. The range, on the other hand, is all the possible y values. So the range of this function, well, the y values go as low as negative 9, and they go as high as forever. So the range here is negative 9 to infinity. And that's one way, if we're able to graph a function, that we can see what the range is. 2 things about this. One, maybe just one thing. It's not always easy to graph a function, right? Sometimes, and even if we can graph it, sometimes it's really kind of hard to actually see where the bottom of the range is. For example, I've got an example, right? If you had something like y equal to x to the 4th minus 4x cubed, which looks something like this. We don't yet, although we will eventually. Oh, sorry. One second, Gabriella. We don't yet have the ability to figure out what the bottom value is here, although we will have that in a minute. Yeah. So this one, we were finding the range ended up being negative 9 to infinity. So here's what I want to do next. Oh, sorry. Is that enough time, Gabriella? We good? Okay. So something like this, we don't really have the tools yet to find the range, although you can totally graph it on Desmos and figure out what the bottom point is. But what I do want to do is talk about how I find the range of something like this. F of x equal to 6x plus 1 over 2x minus 7. And so what I want to say is the way we're going to find the range of this is actually by finding the inverse function. So before we find the inverse, let's talk about finding the domain. So again, remember that the domain is all the possible x values. Here, the only issue is the possible division by 0. So for our domain, we're going to exclude 2x minus 7 equal to 0, which is going to be 2x equal to 7, x equal to 7 halves, or if you prefer, 3.5. So our domain would be negative infinity to 7 halves, union 7 halves. For the range, so we could graph this one, but it's a little challenging. So here's what I want to say about the range and how it works with inverse functions. So when you're finding an inverse function, the process typically is to first write it as y equal to 6x plus 1 over 2x minus 7. So I'll remind you, the domain is all the possible x values, which in this case is everything except for 7 halves, and the range is all the possible y values. So if we switch x and y, which is what we do when we find the inverse function, so look, now the domain and the range have switched, right? If we switch x and y, well, now y isn't allowed to be 7 halves, which is the domain, and x isn't allowed to be whatever the range wasn't allowed to be. So what I'm really saying here is that when you switch x and y, you switch the domain and the range. So that when you find the inverse function, if you want to find the range of the original function, it's equivalent to finding the domain of the inverse function. Now, a couple caveats, or one caveat, this only works if you can actually find the inverse of the function. A lot of functions are not invertible. Parabolas, for example, right? I think I erased it. Yeah. This function isn't really invertible because it fails the horizontal line test, right? If you try to switch x and y here, if you flip this across the line, y equals x, it doesn't become a function, right? You fail the vertical line test if you flip it across the line, y equals x. So things that don't pass the horizontal line test are not invertible. But if the function is invertible, which this one is, then you can find the function's range by finding the domain of the inverse, right? Because we want to find what all the y things could be, but y and x change, so now we're trying to find what all the x things can be, which is the domain. So let's find the inverse function. We still have to solve for y, and that's kind of the hard part. So solving for y, we always want to get rid of this denominator. I'm going to multiply both sides by 2y minus 7. So I'm going to have x times 2y minus 7 equal to 6y plus 1. Now we have to solve for y, but y has to be in terms of just x, meaning, I've definitely seen people do this too many times, is we can't just subtract 1 and divide by 6, because then we would have y equal to x times 2y minus 7 minus 1 divided by 6. And specifically, you would have y expressed in terms of x and y, which is a problem. So we have to be able to isolate the y and not have it be in terms of anything except for x. So we have to distribute the x here. So you get 2xy minus 7x equal to 6y plus 1. And then we want to group all of the y things together and all of the not y things together. So I'm going to subtract 6y of 2xy minus 6y. I'm going to add 7x equals 7x plus 1. And now we can factor out a y. So y equals, keep wanting to jump to the next step. So factor out a y, you've got y times 2x minus 6 equal to 7x plus 1. And then finally divide by this, 7x plus 1 over 2x minus 6. So that's your inverse function. So this is f inverse of x is 7x plus 1 over 2x minus 6. Okay, so now let me ask you guys, what number is not in the domain of this function? What is x not allowed to be here? You can type it in the chat. It's one key. Just had an idea. So I'm going to start next class. I'm going to start trying to, when I ask you guys a question, to type in the chat. I'm gonna have you work on it for like 30 seconds and then have everybody write their answer. So everybody has a chance to, not that I don't appreciate your answer, Marshall, I do appreciate it, but it's always the case where like one person answers it and everyone else is like, okay, well, there's an answer, so we don't need to say so. So the next time I want to ask the question, I'm try and give you guys a little bit of time so that everybody can write their answer in the chat. But yes, x can't be 3 here, but remember, x and y switch, so we're really saying that the y of the original function can't be 3. So y can't equal 3. That is, the range can't have 3. So the range of this function is the same as the domain of its inverse, which is everything except for 3. Now, this is totally true, and we don't really need to have to, what's the word I'm looking for? We don't have to do any more verification, but I really want to show you that this function actually can't equal 3. So if we try and set it equal to 3, so if we try and set, what was it, 6x plus 1 over 2x plus 7 equal to 3, we're going to have problems. Right? I'm going to multiply both sides by the denominator. So 6x plus 1 equals 3 times 2x plus 7. And then 6x plus 1 equals 6x plus 21. And the 6x's cancel. And that is a problem. That's not true. That's not true. That's not true. That's not true. So it can't be 3. In this case, you might also recognize that 3 is a horizontal asymptote of this function, 6x plus 1 or 2x plus 7. And while it is true that sometimes a function cannot cross its horizontal asymptote, sometimes a function can. So being a horizontal asymptote isn't always what's what I'm looking for? It doesn't always mean that you are excluded from the domain or from the range. It just means you often are. Yeah. So yeah, range can't be 3. It can't have 3. So these are the words. These are the 2 typical ways of trying to find the range of a function, either by graphing it and just looking at where the y values are, or if possible, finding the inverse function and finding the domain of the inverse, which is equal to the range of the original. Good to know. All right, what else have I got for these last 11-ish minutes? Oh yeah, composition. Oh yeah, we got some good stuff here. Let's do some graphing, maybe some graphing. Let's look at some compositions, then maybe we'll come back to some graphing. So let's say we've got these 2 functions. Function it up, functions. Can you do a 1-to-1 function problem with a horizontal line test? Yeah, I mean, I know what this, I guess I'm not sure what kind of question we would ask, Marshall. Not that I'm not willing to do it. I'm just not like to asking the question like, is this function 1-to-1? Sure. Sure, okay. So here's a question. So is f of x equal to x cubed minus x 1-to-1? Does that seem, is this kind of what you're looking for? Cool. So how can we tell if it's 1-to-1? There's a couple different ways. So to be 1-to-1, we have to pass the horizontal line test. Another way of saying that is that different inputs have to give you different outputs. So let's look at a couple of examples that we know are not. Or actually, let's look at one example that we know is and one example that we know isn't. We're going to come back to that question, but I want to talk more about the 1-to-1-ness. So parabolas are definitely always not 1-to-1. So here's the simplest one, y equals x squared, or f of x equals x squared. So f of x equals x squared is not 1-to-1. And there's like 3 different ways you can see this. One way is graphically. Obviously, this fails the horizontal line test. Right? I can draw a horizontal line, and it passes through multiple points on the graph. We could also see it by noting that, so to be 1-to-1, there's 2 ways of saying this. They're equivalent, but it's just, they're different. I mean, they're equivalent, but they look different. So one way of saying it is if x1 is not equal to x2, so if you have different x values, the y values also have to be different. Then f of x1 should be different from f of x2. Well, that's not true here, right? I can find 2 different x values, 3 and -3, different values for sure, but f of 3 is equal to f of -3, right? Which is 9. 3 squared is 9. So here you can see, oh yeah, different x values still give me the same y value. And really it's the same as not passing the horizontal line test, because you can think of this point as the point -3, 9, and this point as the point +3, 9. So you can see that if you fail the horizontal line test, it exactly means that there's 2 places that have the same y value that came from different x values, which is failing to be 1-to-1. Another way of saying this, though, is what's called the contrapositive. If not this, then not that. So if f of x1 equals f of x2, then we have to have the x1 and x2 are the same. So if you have 2 y values that are the same, it means you had to actually have the same x value to start with to be 1-to-1. And again, this fails that, right? So people kind of do this one more generally. So you could say, all right, let's say that f of x1 is equal to f of x2. In this case, that means x1 squared equals x2 squared. Well, does that mean x1 and x2 have to be the same? No, they can be opposites of each other, right? So if I solve this, I take the square root of both sides, square root of x1 squared equals the square root of x2 squared. I get the absolute value of x1 equals the absolute value of x2. So x1 and x2 could be opposite signs. So I'm not getting that x1 is equal to x2 necessarily. We have to get that. So these are all the ways we can check to see if a function is 1-to-1. On the other hand, so we'll come back to this, so we're not quite there. We can show that, say, what time is it? Okay, yeah. So that g of x equal to 4x minus 3 is 1-to-1. So we know that it's 1-to-1 because it's a line. The only line that isn't 1-to-1 is a horizontal line. Right? Graphically, a line is going to do this kind of deal. It's definitely going to try to make a line by heart. It's going to do this kind of deal, and we're definitely going to pass the horizontal line test. But we could also show it by showing that either one of these, right? We could say, I often like to use A and B instead of x1 and x2. So we can say, assume A is not equal to B. Then 4 times A is not equal to 4 times B. And 4 times A minus 3 is not equal to 4 times B minus 3. Which means that f of A is not equal to f of B. To me, this feels kind of weird. Like, this is not the typical way people do it. It is usually much more natural to go the backwards direction and say, we're going to try and show that if the functions are equal to each other, then the inputs actually had to be equal to each other. So we're going to, and that's the more normal way, is to assume f of A equals f of B, and then try to show that A has to equal B. So let's see, f of A equals f of B. So that's f of A, or sorry, I started using f instead of G. Sorry, let's call this f. Apologies. So f of a is going to be 4a minus 3 equals 4b minus 3. And then we can see that a has to equal b, right? We can add 3 to both sides. We can divide both sides by 4. So if f of a equals f of b, then a has to equal b, which shows that this function is 1 to 1. All right, so now let's look at this one. The problem with this one is it might be hard to do in any of these ways, actually. So f of x equals x cubed minus x. So let's try what I think is the most normal way, which is to assume f of a equals f of b. And then try to get to a place where you can see that a equals b, or that a doesn't have to equal b. So a cubed minus a equals b cubed minus b. Ugh. This looks unappetizing, but I think I have an. So this is going to get kind of funky. Yeah, I don't know. Here's what I want to do, even though I don't really want to do it. I'm going to subtract b cubed, and I'm going to add a. Do a and b have to be the same? Probably not. We could probably just pick numbers, right? Like a could be 1 and b could be -1. And 1 minus -1 equals 1 minus -1. So it's definitely looking like it's not going to be 1 to 1. I was going to try to do something weird like factoring an a minus b here. I don't know. This seems bizarre. So I might abandon this and just try graphing it because I know what the graph looks like. So if you factor this, it factors as x times x minus 1 times x plus 1. And we can see that 0 and 1 and -1 are all intercepts, which is a pretty good indicator that it's not going to pass the horizontal line test. And the graph looks like this. Definitely fails the horizontal line test. So yeah, it can be relatively challenging sometimes to show a function is or is not 1 to 1, depending on what your teacher wants you to do. Graphing is always a sure bet if you're able to graph the thing, but sometimes graphing the thing can be hard. But here it's pretty clear that, right, 1 is not equal to -1, but f of 1 and f of -1 both equal 0. So that means it's not 1 to 1.